Okay, we're going to take a look at our next lesson, lesson 6, on rotations of 180 degrees, which we kind of talked about in the last lesson. So rotations of 180 degrees are special. Recall that the rotation of 180 degrees around O is a rigid motion, so that if P is any point in the plane, then P, O, and the rotation of P are collinear, meaning again that they are on the same line. So rotations of 180 degrees occur in many situations. For example, the frequently cited fact that vertical angles at the intersection of two lines are equal follows immediately from the fact that 180 degree rotations are degree preserving. So let's go ahead and take a look at that. Using your lesson worksheet, we'll go ahead and use our transparency to kind of illustrate that fact. So for example 1, if you notice that we have two lines, well, if we start at the very beginning and note that our point of rotation is O, and then we have a point P and a point Q that are not O. Well, if we draw a line segment from O to P, and that's going to be our L1, and let's say we draw another line segment from O through Q, and that becomes L2, then what ends up happening is, because we have two lines, we have an angle here, which we're going to call M. Well, if you rotate around O, what ends up happening 180 degrees later is that these are going to map onto what is already there. So this now becomes 180 degrees, which forms that line, and that means that Q prime right here and Q and O are collinear. Well, the same thing with P and P prime and O, those are also collinear. And because we map this onto here, we know that M and N are equal in degrees because, again, rotation is degree preserving that we did in the other lesson. So that's one way to show that when you have 180 degrees, you have angles you have lines that form vertical angles, and it's just the fact that we can rotate that angle 180 degrees. So let's go ahead and recap. We want to show that the vertical angles M and N are equal, which we just did visually. So we let rotation around O be the 180 degree rotation around O. So we're defining our rotation. And what ended up happening is angle M mapped onto angle N. So more precisely, if P and Q are points on line 1 and line 2 respectively, then the rotation around O of P is going to equal P prime, and the rotation around O of Q is going to equal Q prime. And since rotation around O is degree preserving, angle POQ, which was also labeled angle M, maps onto angle P prime OQ prime, which is angle N, and therefore angle M is equal to angle N. All right, let's take a look at example 2. We're going to look at 180 degree rotation around O around the origin of the coordinate system. So let's go ahead and take a look at example 2. And using our transparency again, if we go ahead and trace over P, and the O is our origin, we have this line right here, or this line segment. Well, notice that it is also, if we drop down, it's also going to form a point A on the x-axis. So again, if we take this and rotate it 180 degrees around O, which is the origin, you're going to notice that it again maps onto the opposite quadrant. So now P prime ends up being 180 degrees away. And notice what happens to A prime if it's on the x-axis. It's the same distance from 0, just the other direction. So there's a summary we can say about the points on the coordinate plane. Oops. There we go. All right, so if a point has coordinates of AB, it is generally said that the rotation around O of P is a point with coordinates opposite of A and opposite of B. Remember, we're not calling this negative A and negative B. It is actually, in this sense, going to be the opposite. So suppose point P has coordinates of -4 and 3. Well, then we are going to show that the coordinates of rotation of O, or a rotation around O of P, are going to give us the opposite of -4, which is 4, and the opposite of 3, which is -3. So if P prime is going to be the rotation around O of P, and we're going to let the vertical line through P meet the x-axis at point A, then by definition of coordinates, the coordinates of P are -4, 3, which means that the coordinates of A are -4 and 0. So this means that the distance of A to O is 4. Since rotation is a 180-degree rotation around O, A prime also lies on the x-axis, but on the opposite side of the x-axis from A. Therefore, the coordinates of A prime are 4, 0. Well, next, if we look at angle PAO, we notice that it is a right angle. If rotation around O maps angle PAO to angle P prime A prime O, therefore, angle P prime A prime O is also a right angle, because again, remember that they are degree preserving. So this means that A prime is the point of intersection of a vertical line through P prime and the x-axis. We already know that the coordinates of A prime are 4, 0, so the x-coordinate of P prime is 4 by the definition that lengths are preserved by rotation also. So at the same time, the y-coordinate of P is 3, which means that the y-coordinate of P prime is going to be -3. So all of this together proves that the 180-degree rotation of a point with coordinates -4, 3 is a point with coordinates 4, -3. So they are just the opposite of each other. So generally, the 180-degree rotation of a point with coordinates of AB is a point with coordinates -A, or opposite of A, and opposite of B. All right, go ahead and in your lesson worksheet, go ahead and try exercises 1 and 2. And when you have completed those 2 exercises, continue the video to check your answers. Okay, so you should have exercises 1 and 2 done. Here's what you should have for exercise 1. And again, it's important to note how you answer this. The rotation around O, so rotation sub O, of the original point to -4 is going to equal -2, 4. We don't need to say anything about 180 degrees in here because it's already mentioned in the problem. For number 2, same thing, the rotation around O, or the origin, of -3 and 5 is going to give us 3 and -5. And again, it's already noted that we are rotating 180 degrees. All right, so now go ahead and try exercises 3 and 4. So pause the video, and when you're done with that, continue the video to check your answers. All right, so you should have completed exercises 3 and 4. Here's what you should have for exercise 3. This one's just a drawing, but if we have a line passing through -6 and 6 up here at the top, then when we rotate it, the parallel line is going to end up going through 6, -6. And because it is parallel to the x-axis, that's how we know that this is going to be a horizontal line. For 4, if we say that it's going to be parallel to the y-axis, then our line becomes vertical. And so if we take a line that goes through from 7, 0, and we rotate it 180 degrees, it's going to go through -7, 0. All right, now go ahead and try exercises 5 through 9. Pause the video, and when you're done, go ahead and check your answers. All right, so here we go with exercise 5. When you have a rotation, L is going to end up being parallel to the rotation of L. So if this is L, then this is called the rotation of L, or L prime. For 6, if we are rotating 180 degrees, if it's passing through 4, 0, parallel to the y-axis, then we have a parallel line. L is parallel to the rotation of L around 0. And this is what it should look like. For number 7, here's the answer. It's parallel again. Instead of -1, our line is now passing through +1. And for even a diagonal line, if we rotate that 180 degrees around the origin, it is still going to give us a parallel line that looks like this. And even without the coordinate plane, we can still rotate 180 degrees, and we're still going to end up with the same result, parallel lines. All right, so in your math journal, let's talk about the theorem. Let O be a point, not line, on a given line, L. Then the 180 degree rotation around O maps L to a line parallel to L. So the key point here being that the point of rotation cannot be on the line. So let's prove this, and we're going to prove it by contradiction. To contradict something means to try to prove it not true, and in the end it's going to end up being true because it's not going to work. So let rotation around O be the 180 degree rotation around O, and let P be a point on L. Okay, so now we're talking about a point on L. The rotation around O of P is going to be denoted as P prime. So again, we're defining our variables. Because it's a 180 degree rotation, we know that P, O, and P prime lie on the same line, and we're going to call this now lowercase l. So you should know that after completing exercises 5 through 9, you know that this theorem is true. So we can make it clear that our observations can be proven by contradiction. If we assume something different will happen, that means the lines will intersect. So we're going to see if we can try to prove that the lines will intersect, and we're going to end up that we can't do that. So here is kind of a picture of what we're talking about. We have a line, L, and we have O and P that are on the same line. And when we rotate this, we know that P prime, O, and P are going to be on the same line, and we've called that line L. So we're trying to prove that these two lines are going to intersect, line L and lowercase l. We want to investigate whether P prime lies on L or not. So keep in mind that we want to show that the 180-degree rotation maps line L to a parallel line to L, not that it intersects. So we're trying to kind of contradict the fact that they are going to intersect. So if point P prime lies on L, then at some point line L and rotation of L intersect, meaning that they would not be parallel. If we can eliminate the possibility that P prime lies on L, then we have to conclude that P prime does not lie on L, because remember, rotations of 180 degrees make points that are collinear. So if P prime lies on L, then lowercase l is a line that joins the 2 points P prime, P on L. But L is already a line that joins P prime and P, so L and L, lowercase l and uppercase L, must be the same line. Because again, we're saying if L joins P prime and P, then it has to be the same line that we're talking about. So the lowercase l and uppercase L are actually the same line. But this is trouble because we know that O lies on lowercase l, and if L is the same as uppercase L, then that means O has to lie on uppercase L. But remember, from the beginning of the hypothesis of the theorem, we said let O be a point not lying on the given line L. So we have this contradiction. Based on what we're saying up here, we're saying O lies on L because O is on lowercase l. But at the beginning, we said O is not supposed to be on L, so we have a problem here. So therefore, if that's the case, then it is impossible that P prime lies on L. And what we have proved is that no matter which point P we take from L, we know that the rotation around O of P does not lie on capital line L. But if the rotation of L consists of all the points of the form rotation of P, where P lies on L, so what we have proved is that no point of the rotation of L lies on L. And therefore L and their rotation have no point in common. And if that's the case, if they have no point in common, then these two lines have to be parallel because they're not going to intersect. And therefore, we have proved that when you rotate a line 180 degrees, you form parallel lines. All right, so to summarize, rotations of 180 degrees are special. A point P that is rotated 180 degrees around a center O produces a P prime, so that P, O, and P prime are collinear. When we rotate around the origin of a coordinate system, we see that the point with coordinates AB is moved to the point opposite of A and opposite of B. We also now know that when a line is rotated 180 degrees around a point that is not on a line, it maps to a parallel line to that given line. All right, we'll see you in class.